All right, so we'll go through thermodynamics questions, but we'll specify much on isothermal questions. All right, so we'll also drive the formula itself and other stuffs. So let's go. All right, so we need to know one thing under isothermal. All right, so we know that we know that work is given as negative P, or negative P, which is external pressure, then change in volume. All right, or it can be just the same negative P, then V. All right, so now we'll say change in volume. Mostly pressure is constant. So what you are going to do here is we'll say, since this is our formula, all right, since this is our formula, what you are going to do, we know that from ideal gas law, PV is equal to what? nRT. All right, so meaning that PV, or just P, which is constant in the formula for work, will be given as nR, all right, T, then over V, like that. Okay, so for one more, meaning that the more value will be just one. So for one more, we are going to write as pressure is equal to R T, all right, then volume. So, but we are going to include the number of moles as well, because it play an important role as well in the formula. So what you are going to do here, we replace P is equals to that. So we are replacing now P is equals to that. So this will be negative P, we said we have N R T over V, all right, dV. Okay, so this can be written as negative R N R, all right, T, then dV over V, like that. Okay, so integrating this formula, we are going to have negative N, all right, R T, all right. So the integral part will only touch where dx is, all right. So we'll say dv over v, like that. Okay, so this can be written as, okay, so where we have this is v2 and this is v1, like that. That's the ratio we should have there. So we're going to say negative nr, all right, t. Then when you integrate this one, is as good as us using natural log or just lean, more especially natural log. So we're going to say natural log of V2, okay, over V1, like that. So this is the formula that we will be using, and we can write this as, when we want to use log instead of natural log, we'll say negative, okay, we are putting a certain value, negative 2.303, all right, N R T, all right, then log V2 over V1. So from this, from ideal gas law, those identity to say, we know that pressure 1 to pressure 2, I mean pressure 1 to pressure volume 1, we are getting a constant thing, all right, it's constant. So what you're going to say is, we know that pressure 1, V1 should give us what? Should give us pressure 2, V2, like that. All right, meaning that since this is isothermal, temperature is constant. All right, so I won't talk about temperature. I would have written temperature down there, but what I'm going to do is I'll just make V2, V1 as the subject of the formula. So what I'm going to do is I'll divide by V1. Also this side divide by what? V1. All right, so I'm going to have pressure 1 is equal to pressure 2, then V2 over V1, like that. So I'll divide again pressure 2. All right, so pressure 2. So this goes. So we have V2 over V2 over V1 is equal to pressure 1 over pressure 2. Meaning that where there is V2, V1, we can put P1 over, I mean P2. So that will be the formula we'll be using under these processes. All right, so let's test it. Okay, question 1 says, calculate the pressure volume work done when a system containing a gas expands from 1 liter to 20 to 2 liters against the constant external pressure of 10 atmospheric pressure or atmosphere. So express your answer in calories or in joules. So we must express it in joules. Also in calories we can do it. So what we are going to do here is we are saying we need to know that work is equal to, like we said in the first on the first page, we said is P, all right, then change in volume. So meaning that we have change in volume and the pressure we have is 10, all right. So I'm going to say negative 10, all right. Pressure is always measured in atm, then times change in volume. We have V1 and V2. So V2 is now 2, all right. V1 is Z1, then rate like that. So this will be negative 10, all right. That is just one there. So atm or liter atm, all right. So this is the one we have. So now we need to take it in joules. So how do we take it in joules? We need to multiply it through by, we need to know that one liter atm, all right, is equal to 101.3 joules. So this and this will go. So we are going to have negative 10, all right, then 3 joules like that. So this is what, this is in joules. Then if we were to take in calories, so we can say the same joule now you multiply, you get this to say 1 calories, all right, 1 calo, all right, is equal to 4.814 joules. So you can just put wherever there is joules, then you'll be able to cancel these units. All right. So that's how you can find it in calories. Then let's go to the next question. So the third question say, the second question says 1 mole of an ideal gas at 25 degrees Celsius is allowed to expand irreversibly at a constant temperature from a volume of 10 liters to a volume of 20 liters. Calculate the work done by the gas in joules and calories. So it's the same stuff, just like on the previous page. So what we are going to do here is we'll say what you're going to do here is we'll say work. We know that work is given by, all right. So there was change in volume. So we apply isothermal equation for calculating work, all right. So what you're going to do here, they are even saying at a constant temperature. So meaning this is isothermal. So we said under isothermal, we can use this formula to say negative 2, all right, 303, all right, N R T, all right, then log, since now we have in volume, for volume we said this V2 over V1 like that. Okay, so what you are going to say is we'll substitute those values, all right. So we have one more there, so it's 2.303, all right. So the number of moles is one more, right, then times the ideal gas value now is what? It's 8.314 joules, then over there's kilo, which is Kelvin, then and also moles. Then times the temperature now. The temperature we have is what? Is 25. So you calculate now 25. 25 plus 273. So 273 plus 25. That is giving you 298. So we are saying now 298 Kelvin. All right. Then log. So V2 is what? 20, right? So this is 20 over 10 like that. Okay. So better you put it in the brackets there. So when you punch this, that is negative 2.303 times more. So the moles, see the units the way they are cancelling. This one will go and this one will go. The Kelvin will go and the Kelvin. So only remain the joule on top there. So we are going to say, so this is giving me the value of 1000. So work is equal to 1000 then 0.46 like that. So this is the value it is giving me. All right. So this is work in joules. Then they said you can calculate also in calories. We said, so to calculate in calories, we need to know that 1 calorie, all right, is equal to what we said is 4.184. Okay, so that's the one for calories. So meaning that we can, this is joules by the way, so we can substitute there by saying work is equal to 17,717.46 joules times now. So we are saying we want to have calories. So say 1 calorie, all right, is equal to what? 4.184 joules. So the joules will go. Then we can divide from there. Then you'll be able to find your answer in calories. So let me do it. So 1717 point 46 divided by 4.184. All right. So this is giving you 410. All right. So this is giving me 410.5. So calories or calories. So this is the answer in calories. So that's how you can calculate this one. Simple as that. So let's go now to the next question. Okay, so this question says find the work done. Find the work done when one more of a gas is expanded reversibly and isothermally, all right, from 5 atm to 1 atm at 25 degrees Celsius. All right, so we need to have the data here. So temperature, we have there was change in pressure, all right, and the, the, the process is isothermal. So meaning that we are using the same formula, all right. So the formula would work is equal to what? Using logs, it will be 2 negative 2303, all right? Natural log, which is the number of moles, then gas constant, then temperature, log, change in now pressure, it will be P1 over P2. So we discussed this one from the first formula we derived. So we know what it means, all right? So what you're going to do here is just a matter of substituting. But for temperature, we have 25, right? 25 degrees. So we add plus 273. So this will give us what? This will give us what? 298. So this is 298 Kelvin. Okay, so our temperature should be in Kelvin always. Then the number of moles as well is 1. So it's just a matter of substituting. Then we'll be able to find our answer. All right. So what you're going to do here will say, what you're going to do here is negative 2.303. All right. Then the number of moles now is what? Is 1. So we'll say 1 more. All right. Then times our gas constant we are using is 8.314. All right, joule. Then over there, it's now in Kelvin per mole. All right. So like that. So then times the temperature now is 2 what? 298 Kelvin. Then log, our pressure 1 is 5, right? So our pressure 2 is what? 1. So this, when you punch on your calculator, so you can see the units the way they are cancelling. Kelvin, moles, more will go. So we'll remain with only joules. So how do we do that? How do we do that? So we are saying when you punch that on your calculator, so it will be, it will give you 3,988 joules. So you can also report in kilojoules if you want. So that is, you divide throughout by 1,000. So that will be 1, 2, 3. So that will be 3.9, all right, 88 kilojoules. So this is how you can also calculate this value. So that's about it, this one. So let's go to the next page as well. We see another question. Okay. So another question says, find change in internal energy or just change in energy. Also find which is heat Q and W, which is work. If 2 moles of hydrogen at 3 atm pressure expand isothermally or isothermally at 50 degrees Celsius and irreversibly to a pressure of, in short, there was change in pressure from 3 atm to 1 atm. So we know what to do here. All right. The process is isothermal. So meaning that it is using the formula to calculate work as work is equal to negative 2.303. All right. Then nRT log pressure. Now we have P1 over P2. All right. So that is it. Then what you are going to do here is just a matter of substituting. By the way, we need to convert this 50, all right, to kelvins. So we have 273 there. So what is 50? 50, okay. 50 plus 273. So that is 3, that is the, all right, let me calculate. That is 323. All right. So we are saying this is 323 Kelvin. So that's the value we are putting there. So we'll say work is equal to negative 2.303. All right. Number of moles is how many? 2 moles. All right. So say 2 more. All right. So then our gas now constant is what? Is 8.314. All right, joules, then it has the units per, which is Kelvin per mole. All right, so times now our temperature, which is 323 Kelvin. All right, then times log 2. So this is the final pressure. So our final pressure is what? 1. Okay, then our initial pressure, it was 3. All right, so we had 3 as our in. So when you punch that on your calculator, so you're going to get your answer in joules as, all right, your answer in joules as negative 14, all right, 10 like that, then joules. Okay, so this is the answer that you get in joules. Okay, so let me write it properly. So it's negative 1410, all right, joules. So now they are saying calculate work. So I've calculated this one. What about this one? Since this process is isothermal, so when it is isothermal, the process was just at a constant temperature. So it wasn't changing anything. So it was at a constant pressure. We expect only to change in what? Pressure and volume. So what will happen is that if this was isothermal, meaning that inside there, because this energy is related to temperature, so it's 0, all right? Meaning that it is 0, we are going to say, we know from first law of thermodynamics, we say Q, heat added, is equal to what? Change in energy is equal to heat added minus heat removed. Okay, so this heat removed is what we call work. So we are saying work. So this is 0. So we can see that Q now is equal to what? W. So this also Q will have the value as negative 10 joules. All right, so that is it. So that's how we were supposed to calculate this one. So you need to understand the terms such as isothermal, adiabatic, isochoric, all those terms. All right, so then to calculate another question, let's go on the next page. So we have the question says 1 gram of water at 1 gram of water at 373 Kelvin is converted into steam at the same temperature. All right, same temperature. So the key word is here is same temperature. All right. So what you're going to do here is the volume of water becomes 1671 moles on boiling. Calculate the change in the internal energy of the system. If the heat of the evaporation is 540 calories per grams, it's 3 marks. So what you're going to do here is, this question was quite tricky, but what we need to know is that our work will be given as negative P, all right, or just work will be given as P times volume, all right. So say P times volume, all right. So from there, what we know that what we need to know is that from ideal gas law, we know that PV is same as nRT, because we are lacking the data such as the change in volume we don't have, or just the volume itself. Then the pressure also we don't have the data, you get. So what we are going to do is we equate to this. We'll see what will happen. So in this case, our work will equal to nRT. All right. So do we have the number of moles? Yes, we can calculate the number of moles by using what? Um, by using this 1 gram. So we say with this 1 gram, all right, divide by the molar mass, which is the mist of water, that is 18, all right, 18 grams per mole, which will just mean we have also, in short, the gram will cancel. We're calculating the number of moles will result into more, all right. Then times the gas constant. Now this one is just constant, so this is 3, all right. So this is 314 joules, then kilo, Kelvin per mole. So then what we need to substitute now is now the temperature. So our temperature is now what? 373. So 373 Kelvin. You see? So what we are going to have now, let's punch it on a calculator. So the Kelvin will go, and also the mole will go. Will remain on with the joules. Okay. So when you punch that on your calculator, you are going to have by the way, I'm not supposed to use this one. I'm not supposed to use this one. This will result into since I'm seeing a measure of calories, so I'm using a certain gas constant now. Okay. So I will use a certain gas constant, which is 2 calories, or um I'll just say sometimes it can be given as 1.987. Okay, so this is calories per something, so per mole or per something. So in this case we have per gram. Okay, all right, so per grams, then there's also Kelvin there. This can be sometimes per mole, now it's now per gram. So what we do here is just so what we it's fine guys, I'm okay, thank you. So what you're going to do here is the more now will go, all right, then and also the grams that we have, so it will cancel. So what we are going to have is we'll use this calorimeter value. So this will give us, when you punch that, it is going to give us 41 calo. So it is 1 gram, so meaning this is the per gram. All right, so now that we have this, the question says calculate the change in the internal energy, and the formula for calculating change in the internal energy is equal to, all right, is equals to heat added minus heat removed, or work removed. So then we have our Q there is now, they said if the heat of vaporization, so this is the heat, so we are saying this is 540, all right, calo per gram, all right, then minus, we have now our work as 41 calo per grams, all right. So now meaning that the change in internal energy will be equal to um the change that will be now 499 calories per gram. So this is the change in what? In internal energy that they wanted us to calculate. So let's go to another question. Okay, so another question says a gas contained in a cylinder fitted with frictionless piston expand against constant external pressure of 1 atm from a volume of 5 liters to a volume of 10 liters. In doing so, it absorbs 400 joules of thermal energy from its surrounding. Calculate. So in short, we know that change in internal energy or change in energy is equal to the heat from first row, guys, minus this, minus work, which is the work heat added or energy added. So what we need to know is that we'll calculate wake using isothermal condition, and the Q is given, then we'll be able to calculate everything. So the work here we can see expand against at a constant external pressure. All right. So what you are going to do here is, we know that since this is not isothermal case, so we know that work is equals to um, negative P, all right, dV, if you were to say like this. So there was change in volume. So what we are going to do is we have 1 atm there, right? So we say 1 negative 1 atm times the change in volume. Now we had initial as 5, then final as 10. So 10 minus 5, that will be 5 liters. Okay. So this will just give us negative 5 liter atm. All right. Okay, so this one can be also calculated in joules. This is liter ATM. So in joules, we'll say negative 5, all right, times, let me just bring this liter ATM. We need to know that 1 liter ATM liter is equal to 3, not 3, is equal to 101.3, so 101.3 joules. So this goes with that. All right, so we multiply now. Negative 5 times 101.3. So that would be now 506.5 joules. All right, so now we come here, we have heat and everything, work we have also. So we'll say change in energy is equals to heat now absorbed is what? 400. So we'll say 400 joules minus, okay, we have our work now that we are from Kake. By the way, it's supposed to be negative. So negative must be maintained. Then plus this negative now, we are saying this is negative 506.5 joules. Okay. So this is 400 joules plus 506.5 joules. Okay, so change in energy is equal to, when we add this, we are going to get 906.5 joules. All right. So this is the number of joules that we have. So this is the number of joules in the change of internal energy. So this is how you are supposed to approach this question. Thank you very much. Let's check if at all we have other questions under isothermal. Okay. So the other question says, calculate the maximum work done when a pressure of 10 grams. So this is the pressure of 10 grams. Hydrogen is reduced from 10 to 1 atmosphere. So we have the change in pressure from 20 to 1 atm. Okay. At a constant temperature. So meaning this is isothermal when it's constant temperature, right? Then the gas behave ideal gas. Then will there be any change in internal energy? This is our question. And also we'll calculate Q. So if this is the isothermal, I've seen constant temperature there, meaning that change in internal energy will be 0. All right. There's nothing, because the temperature which holds the change, it is now constant. So we can't have anything relating to inside the system. So what we are going to do here is just a matter of calculating work. So work, we know that under isothermal, it's given as negative. I like using for logs. So you can also use for natural log. So N, R, T, then log. So this was change in pressure. So this is P1 over P2. We saw how we calculated this formula. I mean, we came up with this formula. So what you're going to have is just a matter of substituting, all right? Then times the number of moles. Now we have 10 grams. So 10 grams with hydrogen. Hydrogen, so moles is equals to the mass given, which is the molar mass over Mr. All right. So more of hydrogen is now, we have 10 over is 2, by the way. So that will be 5 moles. Okay, so this is now 5 moles times Now I like using this one, this gas Dani for calories, which is 1.987. So I like using the original gas constant, which is 8.314 joules over, okay, Kelvin times mole. Then times this now temperature we have there. Our temperature is now 273 Kelvin. So this is 273 Kelvin. Then log our, so our final is now what? Is 1. So we are saying our P1 that is 20, right? Over 1. The final is 1. So we are writing P2 as that. So then from there, it's just a matter of punching. Then when you punch that on your calculator, you're going to have work as -3, right? So -34,000, all right, and 3. So then 0.52 joules. Okay. So from there, then this is our work. And from first law, we know that change in energy or internal energy is equal to the heat added minus the heat removed. So meaning that yes is 0, like we said under isothermal. So Q minus W. So Q is equal to W. So this is also W giving us -3 um 34,003, then 0.52 joules. All right. So this is how we are supposed to calculate this one. So let's go to the next question if at all we still have. Okay, so this marks the end. Please watch out the next part of thermodynamics, which is adiabatic driving the formula, everything like that. So as for now, we end here. All right. Thank you very much. You can share to your friend if you have liked the video.